Welcome to the Deep Dive, where we unpack complex ideas, cut through the noise, and get straight to what really matters. Today, we're diving into something almost universally beloved, that crisp, refreshing glass of juice. But here's the surprising truth many of us grapple with. Despite its natural origins and that healthy halo, fruit juice can often pack as much sugar as a can of soda. It's a real head-scratcher, isn't it?
It absolutely is. You're reaching for what you think is a healthy choice, maybe something full of vitamins, but bam, you're getting a significant sugar hit, often rivals a sugary drink you'd actively try to avoid. And this isn't just like a personal dilemma for health-conscious folks. It puts immense pressure on the entire beverage industry to innovate.
That's really the heart of the problem, yeah. And that's precisely what we're diving into today, a fascinating new approach that promises to sort of flip this dilemma on its head. We're going to explore a recently patented technology. It's developed by a company called Blue Tree Technologies, and it aims to dramatically cut down on sugar in beverages. And here's the kicker. It's not by diluting them or adding artificial sweeteners, none of that, but by selectively removing the naturally occurring sugars themselves. So our mission today is to cut through the technical jargon of the patent, understand exactly how this process works, why it's different from previous attempts, and what it could mean for the future of our favorite drinks. We're drawing all our insights from U.S. Patent Application Publication No. Wait, U.S. 2021-015127, A1, published back on January 21, 2021. So let's get into the sweet problem first.
Yeah, okay. It's important to first grasp the sheer scale of this sweet problem. I mean, the global fruit juice market is enormous, and it's constantly growing. We're talking about 44 billion liters back in 2016, with projections hitting maybe 49 billion by 2022. And just orange and apple juices alone, they make up about 55% of that whole market. Huge numbers.
Wow, that's an incredible amount of liquid. And you touched on the health paradox earlier. Juices are, typically seen as healthy vitamins, minerals, all that good stuff. But they also contain a high sugar concentration, usually around 8 to 10 grams per 100 milliliters. Just for context, like a can of cola is often around 10, maybe 11 grams per 100 milliliters. So very similar. The main sugars naturally in juice are sucrose, fructose, and glucose.
Exactly. And if we connect this to the bigger picture, this kind of high sugar consumption is a pretty significant contributor to public health challenges, things like obesity, diabetes. So the pressure on the industry to deliver genuinely healthier options is, well, it's only intensifying.
So, okay, with that persistent problem, what have people tried in the past? And, why didn't those solutions quite hit the mark?
Well, the current low-sugar beverages you see often resort to fairly simple solutions. Things like mixing juices with other less sweet drinks, maybe coconut water, or just diluting them with plain water. Or, of course, they introduce low-calorie artificial sweeteners. The big problem with these approaches is they fundamentally change the juice itself. They don't maintain the same natural sensory and nutritional characteristics, and often you end up with a pretty long list of additives on the label, which people don't always love.
Right. You're not really getting that pure juice experience anymore. So what about more direct sugar reduction attempts? Have those been tried?
Oh, yeah. Historically, those have been pretty problematic, too. Think about non-specific resins. They'd remove sugar, sure, but they'd also strip away the juice's natural acidity, mess with its taste, its smell, even its color sometimes. You'd end up with something that barely resembled juice.
Okay, so not ideal.
Not at all. Then there were chemical methods, like adding enzymes to make sugars non-digestible, or using non-alcoholic fermentation. These just completely altered the juice's natural environment and, importantly, its flavor. And then you have expensive filtration systems, like ultrafiltration or reverse osmosis. But they're not really designed specifically for sugars. They negatively impact the quality, and honestly, they're just not commercially practical for large-scale juice production. Even with something like milk, which naturally contains lactose. Creating lactose-free versions usually involves breaking the lactose down into other sugars, like glucose and galactose, using enzymes. It doesn't actually remove the sugar, it just changes its form.
I see.
Oh.
So this is where Blue Tree Technologies comes in with what sounds like a genuinely novel approach. The core innovation here, as you said, is to selectively remove naturally occurring sugars in a way that's effective, affordable, and scalable. That's a huge promise.
It really is, and the emphasis is definitely on maintaining purity. The goal is to do this without mixing any non-natural chemical substances into the beverage, and without significantly changing its chemical composition beyond, removing the targeted sugar molecules themselves. Maybe some organic acids for balance, but that's about it. It's all about subtraction, not addition.
Okay, subtraction, not addition. I like that. And what sugars are they primarily targeting with this kind of precise selective removal?
They're primarily going after the bigger, more complex sugar molecules, the poly or disaccharides, so things like sucrose, which is
Mm.
basically common table sugar, and lactose, which you find in milk. But the beauty is its versatility. The method is designed for natural fruit juices, especially the popular ones like orange and apple, both NFC, not from concentrate, NFC from concentrate, but also vegetable juices and even other beverages like milk.
So it's not just a juice thing. This could potentially transform a whole range of drinks.
Yeah.
That's interesting. And how much sugar are we talking about removing here? Can they just eliminate it entirely? Or
Yeah. Well, the process typically achieves a pretty substantial reduction, usually in the range of 30 to 50% sugar reduction in the final product. But depending on the application and the desired outcome, it can actually range anywhere from 15% up to an impressive 75%. So there's flexibility.
That's incredible flexibility, yeah. And where does this fit into the existing beverage manufacturing process? Is it like a whole new line they have to build, or can it slot in?
That's actually one of its key strengths.
What?
This technology can be incorporated at pretty much any stage of a juice manufacturing process. Could be before or between filtration, pasteurization, filling, bottling steps, wherever makes sense. For clear juice, it's usually after they've separated the pulp or done the initial filtration. For concentrates, it can be done before or after concentration or even after reconstitution. This adaptability makes it much easier for existing manufacturers to potentially adopt it.
Okay, let's unpack this a bit more then, because this is where the real ingenuity seems to lie. The patent talks about a first adsorbent as the star player. How does it actually work? What's the magic?
Right, the first adsorbent. It's essentially a material that has a very high selectivity for polysaccharides, specifically those disaccharides we mentioned, like sucrose and lactose. Think of it almost like a molecular magnet, but one that's only strongly attracted to certain types of sugar.
And here's where it gets really interesting for me, the unique mechanism. It's not just a basic filter, is it? It's about structure recognition. That sounds super sophisticated.
It is pretty sophisticated, yeah. The selectivity isn't random at all. It's based on a combination of things. Non-covalent bonds, which are weaker chemical bonds, and what they call structural matching. So imagine the adsorbent material having this specific microstructure, like tiny holes or cavities. These act as sugar receptors, and they're specifically designed to physically fit and bind only certain sugar molecules. It's kind of like a lock and key system, but custom made for sugar molecules.
A lock and key for sugar. Got it. And the primary material for this amazing adsorbent is zeolite. That's a natural mineral, isn't it? I think I've heard of it.
It is, yes, a naturally occurring mineral. And what's crucial here is getting its chemical makeup just right for this job. They use specific types of Y-zeolite, often in their H+ and calcium forms, and they need a precise silicon to aluminum molar ratio. They found that a ratio of at least 10:1 works well, and you can go up to 30:1 or even higher. Below that, like some zeolites with a 5:1 ratio they tested, the adsorption was negligible. It just didn't grab the sugar. So it's really about engineering that perfect key structure for the sugar's lock.
So the precise chemistry really matters a lot. Okay. And crucially, what exactly does the zeolite bind to? Does it just grab all the sugars indiscriminately?
No, and this is absolutely critical. These specific zeolites mainly adsorb sucrose. That's the real scientific sleight of hand here. They practically do not absorb citric acid, which is vital for the juice's tartness, its flavor. And they also don't significantly adsorb the monosaccharides, glucose or fructose. This is absolutely key for maintaining the juice's other characteristics, its acidity, its overall flavor profile, beyond just the sucrose content.
Wow. So they're literally engineering the juice at a molecular level, picking out just the sucrose. It's almost like a, I don't know, bespoke tailor for your drink, isn't it?
Yeah, that's one way to put it.
But how do they actually make this zeolite powder usable in a large-scale system? It can't just be loose powder floating around, surely.
No, that wouldn't work in a practical system. The zeolite powder is cleverly embedded in or coated onto food-grade beads. These beads are designed to be quite small, typically ranging from maybe 0.1 up to 15 millimeters in diameter. And they have internal pores ranging from 0.1 to 100 micrometers. They can be made from various food-grade materials like hydrogels, think alginate, which comes from seaweed or organic resins, glass, polymers, carbons, or ceramics. Lots of options. This basically makes the zeolite easy to handle and incorporate into a flow system, like a column.
And as I was reading through the patent, something else jumped out at me that's just so clever, almost whimsical. These beads can actually change color to show how much sugar they've absorbed. Imagine that in a home-use device, like a visual cue telling you your juice is getting healthier.
Yeah, it certainly adds a practical and visually intuitive element. It could be great for consumers. And the reason this whole system is potentially so sustainable and economical is the regeneration cycle. Because the binding relies on those weaker non-covalent bonds we mentioned, the captured sugars can be released fairly easily. This allows the adsorbent beads to be reused. Typically, they say 10 to 100 times, but potentially even up to 1,000 times or more.
Wow.
Think of it like a reusable coffee filter, but for sugar. Instead of throwing it away, they simply rinse the sugar off, and it's ready to go again.
Okay, so once the sugars are bound to the adsorbent beads, how do they actually get them off and prepare the adsorbent for reuse? This is where the hydrolysis unit comes in, right?
Yeah.
Yes, exactly. After binding the sugar, the adsorbent moves, or the flow changes, into what they call a hydrolysis unit. And here, the bound polysaccharides, the sucrose, basically are broken down into simpler monosaccharides, so glucose and fructose. This is done primarily by heating the adsorbent itself. They use temperatures of at least 40 degrees Celsius, typically around 60 C, but it can go up to 110 degrees Celsius depending on the specific setup and the adsorbent.
Okay, and why heat? Is it just to release the sugars, or is there more to it than that?
Well, the heat serves a kind of dual purpose. It definitely helps release the sugars from the binding sites, but it also activates the catalytic properties of the adsorbent material itself, the zeolite. This actually promotes the hydrolysis reaction. It helps break down the sucrose molecules into glucose and fructose. They mentioned that enzymes like invertase can also be added to enhance this process if needed. And this thermal hydrolysis approach allows for efficient sugar release without needing to add significant amounts of water, which is important, especially if they're processing juice concentrates. You don't want to dilute it unnecessarily at this stage.
Right, that makes sense. So once the sugars are hydrolyzed broken down, how are they actually removed from the adsorbent so it can be reused?
So the adsorbent is then washed. It's rinsed with a solution, often just pure water, or sometimes even a solution that already contains some of the recovered fructose and glucose. This wash step effectively flushes away those now hydrolyzed monosaccharides, the glucose and fructose from the adsorbent beads.
And this wash, it yields a sweet byproduct, doesn't it?
Yeah.
So it sounds like nothing actually goes to waste.
That's exactly right. This wash water, which they call the eluent, now contains all those separated sugars, fructose and glucose in the case of juice, or glucose and galactose if they were processing milk. And this isn't just waste, it's actually a concentrated, sweet byproduct. It could potentially be purified and sold, creating an additional revenue stream and making the whole process even more efficient and sustainable.
Very clever. Okay, so let's try and put it all together now. Let's visualize how this system would actually work in a real-world scenario, like in a juice factory. What are the different ways this sugar removal process can be set up?
Okay, first things first. Before any sugar removal magic happens, the solid components, like pulp in orange juice, they have to be separated out, usually through something like centrifugation or filtration. Interestingly, they noted that directly contacting natural orange juice with zeolite can actually cause the pulp to precipitate out, sort of clump together. So that initial separation is definitely needed.
Okay.
But the good news is the pulp isn't lost. It can be optionally reintroduced later to the treated juice if you want that pulpy texture back.
Gotcha. So a basic system would probably just have one adsorbent, the zeolite one. How does that flow?
Yeah, in its simplest form, you'd have the untreated juice go through that initial solid separation step, get the clear liquid. That clear liquid then passes through a column packed with the zeolite beads. The zeolite selectively grabs the sucrose. Then the treated lower sugar juice is collected at the other end. And meanwhile, or afterwards, the zeolite column that's now full of sugar is regenerated using that hydrolysis and washing process we just discussed, getting it ready for the next batch or cycle.
Okay, that sounds straightforward enough. But what if you want to remove more than just sucrose? Or maybe manage other aspects of the juice's composition, like acidity? The patent describes a more advanced system using dual adsorbents.
Exactly. This is where it gets even more sophisticated and allows for more control. The system can incorporate a second adsorbent. This second one is often an organic ion exchanger, like a resin. They give the example of Doex-99 cow resins. And the second adsorbent column can be placed either downstream or upstream of the main zeolite column, depending on what exactly they want to target.
And what's really interesting is how these different adsorbents target different things. You mentioned the Doex-99K resins, for instance, showed better adsorption efficiency for fructose compared to sucrose or glucose. So is it a tag team effort?
Precisely. It allows for a much more comprehensive sugar removal profile if needed. So the combination of both inorganic adsorbents like the zeolite and organic ones like the resin ion exchangers gives them really precise control. They can selectively remove different sugar molecules or even target sugar molecules and specific organic acids like citric acid if they want to adjust the overall taste balance.
Very customizable. Now, when it comes to operating these systems in a factory setting, are we talking about a continuous flow process running 247, or is it more like a batch process?
Both are possible, which is another advantage for industry adoption, I think. For large-scale continuous flow, the process can run using multiple columns filled with the adsorbent beads. So when one column becomes saturated with sugar, the juice flow is simply redirected automatically to a fresh second column while the first column goes offline for regeneration. They can even arrange this in a really sophisticated setup called a simulated moving bed, or SMB system, which is known for high efficiency in separation processes.
Okay, SMB. Or for maybe smaller operations, there's a batch process option.
Correct. For a batch approach, it's simpler. The adsorbent beads can just be mixed directly with the beverage in a big tank or container. After enough time for the sugar to be absorbed, the beads either settle to the bottom, or they might float if the beverage itself is denser, and then the treated lower sugar beverage is simply drained off or removed. Then the beads are harvested from the tank and taken away for regeneration. So yeah, it's quite flexible depending on the scale and needs.
Right. So, okay, the goal isn't just to remove sugar, but crucially, to do it while keeping the beverage tasting like itself.
Yeah.
That's the real trick, isn't it? Maintaining that sensory nutritional integrity. You don't want it to taste, I don't know, watery or just off.
Absolutely. That's paramount. Simply removing sugar, especially a significant amount, can drastically change a beverage's taste profile, its mouthfeel, everything. So this technology is really precisely engineered, aiming to preserve those desired sensory characteristics that consumers expect from, say, natural juice.
And a key measure of that taste balance in juice is the Brix acidity ratio, right?
Yeah.
The sweetness versus sourness. Can they maintain that balance effectively?
Yes. And this is fascinating. They state that the treated beverage can maintain a Brixidity ratio that's very close to the original, usually within plus or minus 20%, and often even tighter, like plus or minus 10% compared to the untreated juice. This can be achieved partly by the selective sugar removal itself, but also potentially by lowering the acidity of the treated juice slightly, or even specifically removing some organic acids like citric acid from orange juice. And they can do that either with the same sugar receptors on the adsorbent, if they have some affinity, or by using different acid-specific adsorbents in the system, perhaps that second column we talked about.
And they can even make strategic pH adjustments during the process itself to optimize things, can't they?
Yes, quite cleverly. They mentioned that the pH of the juice portion that's actually undergoing the treatment can be temporarily increased, maybe above 4.5 or 5 before the sugar separation step. Doing this can actually optimize the selectivity and the kinetics, the speed of the sugar removal. Yet, the final reduced sugar product's pH can still end up in that preferred natural range for juice, say between 3.5 and 4.5.
Okay, this next part I found really clever. The process is apparently designed to remove relatively more sucrose and less fructose. Why is that important? At first glance, it feels a bit counterintuitive if you just want to cut sugar.
Yeah, it does seem a bit counterintuitive, but it's actually really smart sugar removal. It's important because fructose, one of the main remaining sugars, actually has a higher sweetening power than sucrose does, gram for gram. So by retaining relatively more of the fructose while significantly reducing the sucrose, they can maintain a more balanced and satisfying sweetness profile in the final product, even with a substantial overall sugar reduction. They mentioned this can result in a final sucrose to total sugars ratio, potentially as low as 10 to 30%. It's about optimizing the experience of sweetness for the consumer, not just crudely cutting the grams.
Ah, okay. So it's not just about less sugar. It's about smart sugar removal. That's a key distinction. And they can customize the end product too, aiming for precise sugar reduction levels, right? This feels less like industrial processing and more like a chef creating a custom dish sometimes.
Exactly. They have multiple levers they can pull to fine-tune the final product. For instance, A portion of the treated low-sugar juice can even be blended back with some of the untreated original juice. This allows them to achieve a very precise, desired sugar reduction level overall, maybe targeting exactly a 30% or 50% reduction, whatever the product goal is.
Right.
And remember, that pulp removed at the start, that can easily be returned to the treated juice afterwards, ensuring you still get that natural mouthfeel and texture if it's, say, orange juice.
And if all that isn't enough to get the flavor exactly right, they've got even more options in their toolkit to make it taste perfect, don't they?
Yes, absolutely. They can strategically add natural, low-calorie sweeteners if needed. Things like date, stevia, agave fruit, honey, apple extract, erythritol, monk fruit like sweet tango or maple. And beyond just sweetness, they can also use natural masking agents or flavorings. Things like cinnamon, chocolate, vanilla, strawberry, coconut, ginger, licorice. These can be added to correct any subtle taste changes or maybe mask any slight bitterness that might arise from reducing the sugar so much. It really is about ensuring the consumer loves the final taste.
And they can even blend different types of juices together post-treatment to achieve a desired profile, right?
Precisely. You could take a treated citrus juice, like orange or grapefruit, which might still be quite acidic, and blend it with lower acidity non-citrus juices, maybe mango or carrot juice that's also been treated. This lets them achieve a specific desired pH level and create novel, balanced taste combinations. Really opens up possibilities for new juice blends.
And it goes beyond just taste and sugar content, doesn't it? This technology seems like it really opens the door for creating a new generation of functional beverages.
It absolutely does. Once you have this precisely engineered low-sugar base beverage, you can think about adding other beneficial ingredients. Things like minerals, iron, calcium, sodium, or proteins, maybe caffeine for an energy drink, or even probiotics for gut health. These can all potentially be added to create tailored functional beverages that meet specific consumer health needs or preferences.
And here's a really cool application that takes this whole concept beyond the factory floor. The patent mentions this technology isn't just for massive industrial scale. It could potentially be used in standalone devices for end consumers, maybe in home or office settings. You could imagine those sugar-removing beads, perhaps in a porous bag or cartridge, that even indicate the sugar removal via that color change we talked about. You could literally watch your juice getting healthier right on your counter.
That really brings the innovation full circle, doesn't it? Making it potentially accessible right at a personal level. It moves from large-scale manufacturing to something you could maybe integrate into your daily routine at home. Very interesting potential there.
So wrapping this up, we've just explored a truly innovative approach to tackling that big sugar dilemma in many of our favorite beverages. By harnessing the power of these selective adsorbents like zeolites and combining it with precise hydrolysis for regeneration, this technology offers a genuine pathway to significantly reduced sugar content. And crucially, doing it without necessarily compromising the natural essence, the taste, or the nutritional value of things like juice and milk. It's a really sophisticated blend of chemistry and engineering, almost turning everyday drinks into a canvas for scientific precision.
Yeah, and if we connect this back to the bigger picture, this kind of selective, non-additive sugar removal technology, it really raises an important question, doesn't it? How might this reshape our very definition of what constitutes a natural beverage in the future? If you're just taking something out, is it still natural? And maybe more excitingly, what entirely new categories of customized, health-optimized drinks could this unlock for future consumers? The possibilities seem quite broad.
Absolutely. Imagine a world where your daily juice is tailored not just for flavor, but for a precise nutritional profile, maybe even personalized, and created with such, well, elegant simplicity at its core. It's definitely a fascinating thought to chew on. Thanks for joining us for this deep dive.